Hello, this is Vibhuti from Group 8, and today I'll briefly explain the project Trauma Activation Algorithm that we worked on for 2 semesters for SER518. The project that we worked on was designing an evidence-based trauma activation algorithm for Phoenix Children's Hospital for minimizing the overutilization of Level 1 pediatric resources. When I say overutilization of Level 1 pediatric resources, there have been instances in the past when a Level 2 trauma was identified as a Level 1 trauma, and for treating a minor femur bone injury, a team of 20 doctors was activated, which is nothing but over triage. The existing trauma activation algorithm used ACS 6, that's American College of Surgeons 6 criteria, which resulted in over triage and increased costs. The purpose of this 2 semester long capstone project was designing an algorithm and reducing the over triage. Now, diving straight into the implementation part of the project, since we had to train the model using machine learning algorithms, the data for the same was provided by the sponsors. The further steps included performing dimensionality reduction using principal component analysis to determine the most significant pre-admission factors, followed by implementation of classification algorithms such as logistic regression, decision trees on subcategories of data. We divided the data into subcategories depending on the type of trauma, such as motor vehicle crashes, fall accidents, and others. We alternatively applied decision trees and logistic regression on the categorical data and decided to go ahead with the one that led the maximum accuracy. As in our case, logistic regression worked best for motor vehicle crashes and decision trees for falls. Once we had the models ready, we worked on optimizing the models to improve the accuracy by tuning the parameters, which is also known as hyperparameter tuning. We used various imputation methodologies for imputing the missing data. We also used k-fold cross-validation for optimizing the models and computed the accuracy scores for under and over triage. Our project was more research-oriented and involved designing algorithms and coming up with the accuracies. For achieving higher accuracies and minimizing the over triage, we divided our data into categories depending on the type of accidents as fall, motor vehicle crashes, and others, such as assault. The following table shows the percentage of over and under triage before and after the optimization. For an instance, the percentage of over triage for logistic regression for motor vehicle crashes was initially 81% and was reduced significantly to 44%. Similarly, for decision trees, it was 79% initially and was reduced to 5%. We also need to take into account the percentage of over triage, which was initially 76% for motor vehicle crashes and was reduced to 33%. And decision trees, it was 82% and was reduced to 57%. Similarly, if we look at falls, the under triage percent was 83% and was reduced to 1.5% after optimization, and over triage was 84% and was reduced to 1.9%. As we can see from the figures, the percentage of over and under triage have been reduced significantly after applying the optimizations. While testing the performance of our algorithm, we also took into account specificity and sensitivity. Sensitivity, as defined for our algorithm, is the ability of the model to correctly determine the number of level 1 trauma types, while specificity is the ability of the model to correctly determine the number of level 2 trauma types. The table shows the sensitivity and specificity for the categorical data when different classification algorithms were applied. As we can see, for logistic regression in the case of motor vehicle crashes, the sensitivity is 63%, which states that 63% of the times the logistic regression model was able to correctly determine the number of level 1s, and 96% of the time it was able to correctly determine the number of level 2s. While if we see for falls, the sensitivity is 25%. That means only 25% of the time the number of level 1s were correctly determined by logistic regression, while it was 39% correctly determined by decision trees. And the specificity being 98% for logistic regression means the number of level 2 trauma types were correctly determined 98% and only 82% for decision trees. And similarly for all the other injury types. Our project, being a machine learning research-oriented project, had a lot of functional requirements which involved providing statistical information about the data besides generating the evidence-based algorithm. The figure below demonstrates the categorical trauma population as a percent of total trauma population. As shown in the figure, the total trauma population was 17,369, out of which only 16,237 was blunt trauma type. Further subcategorizing into level 1 and level 2, 4,943 were classified as level 1 and level 2 trauma population, which being further classified as 6,652 being fall trauma type, 3,101 being motor vehicle crashes, and 1,119 being the other trauma types. Figure 2 on the right shows a pie chart representing the categorical trauma types as a percent of total trauma types. As we can see from the figure, almost 64% of the trauma types were classified as other trauma types such as assault, followed by fall, which constitute almost 21%, and motor vehicle crashes, which makes 13% of the total. An important part of our research towards building the trauma activation algorithm was finding the correlation between the various pre-admission factors. The heat map shows the correlation between the various pre-admission factors such as age, gender, respiratory assistance, etc. As we can see from the figure, there isn't any strong correlation between the factors, which was an important part of our findings. Now, moving to the findings, we could find out that logistic regression on injury severity showed almost 100% over-triage, which was actually too much. The ACS6 criteria resulted in an over-triage of 50% and under-triage of 45%, and after applying the classification algorithm that was developed by us, the over-triage was reduced from 50% to 21% and 45% to 42%. And if we just look at the categorical data for motor vehicle crashes, the over-triage percent was 33%, which is definitely less than 50%, and 4% under-triage. For falls as well, it was reduced significantly to 17% over-triage and 13% under-triage. And for other categories, the over-triage was just 13% and 10.16 under-triage. We also found out that there's no strong correlation among the data, and that's why all pre-admission factors are important in deciding the trauma level. To conclude, we concluded that all the pre-admission factors such as blood pressure, heart rate, age, gender, intubation can accurately determine the level 1 activation criteria. Evidence-based algorithms utilizing machine learning tools reduce over-triage significantly. Machine learning classifies patients more efficiently than the ACS6 criteria and the injury severity score, which was initially used by the existing algorithms. Future work might include combining post-admission and pre-admission factors to perform factor analysis and improving factor scores, incorporating second-hand machine learning tools to improve models, and involving big data mechanisms and Hadoop for handling big data. Improving imputation of missing data, validating algorithms in a prospective trial, and developing a mobile application or a web application for emergency medical services. We've already built a prototype of it. Maybe I can just show you the prototype. So this is a web prototype that we've built. You can enter the patient's name and all the pre-admission factors such as gender type, trauma type, field, systolic blood pressure, and if you just click on it, you can get the trauma level. So yeah, and we can also build a mobile application for it. These are the references. And thank you everyone for the wonderful opportunity. It was a great learning experience, and we got to implement agile methodology, which was definitely something new for every one of us. Thank you.